In question 8.1, we've got two circles. We've also got a parallelogram in the mix, and we have a tangent over here to the smaller circle. And with all that, we need to prove that AD is the same size as DE. So let's talk about how we're going to do that. If we have a look at those two sides, we can see they're sitting quite snug inside of a triangle. So if I prove that this angle E1 is equal to this angle A, then that will successfully prove it's an isosceles triangle, and I can conclude that ED will be the same size as AD. Okay, now let's see how we're going to get that done. So I'm going to start off with one of the angles. It doesn't matter which one you start with. I'll just start with A. Now I can see that A is sitting inside of that parallelogram they were talking about. And a certain theorem with the parallelogram states that the opposite angles are equal inside of a parallelogram. So if I look at A and go to the opposite angle here to C, I know that that's going to be a green angle for this reason, op angles of par. So we're going to write it up just like this: angle A equals C, op angles of par. Now I'm going to see what I can do with this green angle, see if I can relate it to E1 somehow. Okay, and then what I'm noticing is that C is sitting inside of a cyclic quad. Yes, would you look at that? So if I just extend this line EB a little, then I can see that E1 is an exterior angle of that cyclic quad. And we know a theorem that relates the exterior angle to the interior opposite angle. It's exterior angle of cyclic quad, which we've seen in this paper quite a bit before. So now I know that this angle C will be equal to E1, and we're almost home safe. So let's get that written up. We're just going to say C equals E1, and then we're going to slap this next to that as our reason. And after we've stated that, we're now going to revisit the triangle we spoke about earlier to wrap this question up. So I firstly need to make the link between these two angles. So we can see they both equal C, so therefore these two have to equal. And we're going to state it just like that. And now we're going to jump into our conclusion. So I'm going to show you the theorem that helps us conclude that AD is equal to DE. It's called sides op equal angles. So how it works is, if you know the angles are equal inside of a triangle, you go to the opposite sides in those triangle and you know that they're equal. So now if I go to the opposite side AD, if I go to the opposite side ED, I know that they're equal for this reason. And we write it up just like this: AD equals ED, sides op equal angles. And what I like to remember is, if I'm like concluding that the sides are equal, that's going to be the first word in my reason. And now I've done what they've asked for. It doesn't matter if the order of these letters are switched around, it still means the same thing. And your 4 marks, first one comes from the statement and reason with a parallelogram. Second one comes from the statement. Third one comes from the reason with the cyclic quad. And the last one comes from this way little reason. In question 8.2, we're going to need to prove that DC is equal to BG. So let's get that marked off a little bit more clearly. I need to prove that these two lines are equal in length. And we're going to start off by looking at DC. Now if you remember, DC is actually part of a parallelogram. And I know a property of a parallelogram with the opposite sides, which is that the opposite sides are equal. So if you've got a parallelogram, this side is equal in length to this side, and this side is equal in length to this side. So now I know that DC will be the same length as BA for this reason, op sides of a palm. Sorry, can you please pass the palm? The Parmesan cheese, bro. And we're going to write that up just like this: DC is equal to AB, op sides of palm. So now, if this length is the same as that length, I just need to prove that this line is equal to that line, and then by default this line will be equal to that line, because they'll all have the same length. And now these two lines are sitting inside of a triangle. And if I prove this triangle is an isosceles triangle, then I can prove that this length is the same as that length. So what that will entail is that proving the base angles are the same. So I need to kind of get G to be a green angle. And if I prove that G is a green angle, then I can conclude these are the same length. So this will have the same length as that, etc., etc. Now let's see how we're going to do that. So I'm going to look at the two lines touching the angle G, and I'm going to follow them backwards some more, and they're going to take me to this imaginary chord. And then from that chord, I'll go up and up some more, and it takes me to C. So I can apply angles in the same segment. It's the bow tie. He's back, my bro. If you want to see the bow tie, it's over there. Quite a classy little gentleman. Okay, so we're going to conclude that angle C's angle is equal to angle G for this reason. Angles in the same seg. And with that out the way, we're going to revisit this triangle we focused on earlier. Now I've got to make the link between G and A. So I've got to state that those angles are equal. So we just write A is equal to G. If you want, you can slap a reason there. So you see how we proved that A is equal to C in the previous question. So we can just say that they both equal to C. Because if you look in this line, G is equal to C. In the previous question, A is equal to C. So both G and A equal to C. So it stands to reason that A and G have to be equal. We've been doing that on our sketch by saying like they're all green angles. Okay, now we can start to cook a little bit. Now, sides op equal angles. So we saw this theorem in the previous question. If I've got equal angles at the base of my isosceles triangles, then the sides opposite them must be equal. So if I see my base angles are equal over here, I'll go to the opposite side, which is BG. And over here, I go to the opposite side, which is AB. And I can conclude they're equal for this reason. And we're going to state it just like this. AB equals BG, sides op equal angles. Now we're almost there. Can you see that AB is equal to BG? And AB is also equal to DC. So it stands to reason that DC must be equal to BG. They all three of the sides have the same length. And we have officially waxed this question. So having a look where the 16 billion marks come from. Your statement and reason saying the op sides of the palm are equal gets you your first mark. The statement and reason get you 1 mark a pop for doing that bow tie that we discussed earlier. And then your 5th mark comes from concluding these sides are equal using sides op equal angles. That reason gets you the last mark. And that officially wraps up this vraagstel, Machana Bean.